Well, I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and this opportunity we just have to meet together and study your creation, Lord. You know my prayer, Lord Jesus. Amen. All right, so let me begin by talking a little bit about geometry again. So we've talked about a metric in here before, right, for a vector space. And we said that a vector space paired with a metric formed a geometry. Some people would say that that's a linear geometry. A vector space paired with a metric is a linear geometry. So we can expand that notion today to talk about a manifold in a more geometric sense. All right, so like we could talk about a geometric manifold. And I'm not sure that this terminology is universal or anything. I'm just searching for a turn of phrase that might be is reasonable. So is manifold M paired with metric tensor field. Metric tensor field. We'll say G. So the way this works is that G at the point P is going to be mapping from TPM across TPM to the reals, right? Which is bilinear, non-degenerate, well, symmetric, and 3, non-degenerate. All right. So if this is the case, then this is actually, well, I guess it's not a geometric manifold. It's really a semi-Riemannian manifold, technically speaking, I suppose. So a Riemannian, which of course begs the question, what do we mean by a Riemannian manifold? What's that? What's that about? So let me show you how to do that. If we cross out the semi like this, and cross out this non-degenerate like that and replace it with positive definite, right? Then what you're looking at is that, GP is an inner product, right? So a Riemannian manifold is a manifold in which, at each point, you have a symmetric, bilinear, positive definite form, which serves as an inner product. All right? So in a Riemannian manifold, you can do things like define the length of a curve, right? So how would you define the length of a curve in a Riemannian manifold? All right, here's a point P, here's a point Q. What's the if this is a Riemannian manifold, if you have a manifold paired with a Riemannian metric is something that is pointwise an inner product, right? Pointwise an inner product, then the distance from P to Q, you could define it to be what? Like the infimum of, oh goodness gracious. All right. Say the integral from 0 to 1 of the square root of g sub p, well, not g sub p, g at gamma of t of gamma prime of t, dt, such that gamma, smooth path with gamma of 0 equals to p and gamma of 1 equals to q. All right? So you could define the distance between points like this in a Riemannian manifold. Right? So what we're really looking at here slipping. Are you? Is it still? Is that factorial problem? Has it sapped your spirit? You give up on it. So does that mean you've given up on life today? Oh, it's all Dr. Schmidt's fault. I'll tell him. Let's see here. What's that? Infimum, like the least upper bound. Greatest lower bound, yes, thank you. So it's the shortest possible distance, but the thing is, it may not actually be attained, so that's why we don't just say minimum, because it could be that we're talking about a manifold that's got like a fuzzy edge. So, it could be that like this is the best you can do, but you can't actually do it because that point right there is missing. Right? But in the limiting sense, that's the distance. Right? So some classical language for this is we can write G is equal to like the sum, say I and J of Gij dxi tensor dxj. Actually, I'm not sure how classical that language is, but that's how we can express a symmetric bilinear tensor, right? In local coordinates, that's what it looks like. So in physics, we might say something like, let me just kind of I want to talk about the different notations. So in physics, you might see something like ds squared is, dx1 squared plus, e to the x2 dx2 squared or something like this. I don't know, whatever. And so, that's a shorthand for saying that your metric is, it's apparently 2 by 2. And so it's got like a 1 here, 0 here, 0 here, and an e to the x2 there, all right? All right, so like Euclidean space, for example. So Rn paired with ds squared equals to dx1 squared plus dx2 squared plus dxn squared, if you don't mind me putting my indices down here for a second. This is the standard Euclidean metric in the classical notation. Right? That's a shorthand for the metric that's got the following form, right? So these are essentially the same thing. Just different notations for the same idea. So you've been thinking about the metric in your calculus sequence every time we did like a arc length calculation, or perhaps also like a surface area calculation, something like that. There you're somehow thinking about the distance as it's understood along an object, right? You're calculating the distance along a curve or the distance along a surface, right? in two different directions together to give you area, you know. So again, a Riemannian manifold is a manifold paired with a Riemannian metric. A Riemannian metric is a smooth assignment of an inner product at each point. Fun fact, any smooth manifold can be given a Riemannian metric. What you do is it's a straightforward construction. You can do it. However, I mean, it's Gram-Schmidt. You start with a coordinate system and like just Gram-Schmidt basically, and that makes it. Well, anyway, I don't know. You guys are killing me. Let's see here. Don't ask me. It is not complicated, but don't ask me today. All right. So, great. This is the metric. Now, so one of the other things I'm trying to get at here is there's a Euclidean metric, all right? And we could pull the Euclidean metric. Yeah.
This is
feedback. Go for it.
The distance formula, anytime the square root, that's supposed to be a function of the root twice, or just the normal way.
Yeah, so like this is basically what's going on here is it's analogous to like when we calculate the square root of like d gamma dt dot d gamma dt in like Calc 3 or something. So you can think of the inner product of v and w, well, the metric of v and w, in some senses, like, I can put some quotes, but that's a way to think of it.
Right.
But notice the of gamma of t dependence is because we may judge the distance between points differently at different points on our manifold. We can have a sliding ruler, like it's not, the notion of distance is different at different points in the manifold. That's a possibility we want to allow. So that
in that case, it would depend on x2. In that case, it would need x2.
Oh, yes. This is exactly, that's a non-constant metric, right? So Euclidean space is Rn paired with the Euclidean metric. As I was saying, that's an example of a linear geometry because it's a vector space paired with a metric. So we have, a constant metric on the whole space. It's kind of boring. What's of course much more interesting is if we have, a non-constant metric. We could even have a non-constant metric on a linear space, on a vector space, right? You don't have to have a constant metric on a vector space. You could have a variable one. That could be interesting. But my larger point here that I want to try to get across to you guys today is like if we have a space, a manifold, there's not a unique choice of metric. We could put different concepts of distance on the manifold, and those would give us different geometries. All right? However, there's a sort of natural induced geometry. Let's talk about the induced geometry. Let's talk about the induced metric for a bit. So basically, this is the pullback metric on a submanifold embedded in Euclidean space. All right. So let's talk about R3 for a bit. So we have ds squared is dx squared plus dy squared plus dz squared, if you'll allow me that notation. But there are other ways we could write this, right? If we wanted to express the metric in like cylindrical coordinates, this looks like dr squared plus r squared d theta squared plus dz squared. In fact, if we were to change the metric to the cylindrical coordinate frame, that's what it looks like. If we were to change the metric to the spherical coordinate frame, it looks like d rho squared plus like, oh man, I don't remember. Phooey. It's in your homework? Is it though?
Should still be r squared d theta squared.
Let's see here. If we're down here, I go up here. So this distance is, so this is like a d phi. All right, so I've got rho squared d phi squared plus rho squared sine squared theta d theta squared. Because this distance down here, if we sweep out a little d theta, this radius is rho sine phi. Sine theta, rather. Or is it sine phi? Sine phi, sine phi. I don't know. It depends on... What? Nothing? Seems like it was something.
I just called it.
Oh, you call... Oh.
I
Oh, she's...
was convinced.
All right. Not sure what just happened here, but I'll allow it. Now, so, of course, if we, if we think about like the sphere, rho equals to r, and we try to think. See, I know I know what I want to write. I just don't know how to justify it. But the g, on the sphere is just going to be the rho is froze out. So when we pull back to the sphere, we're setting, phi equal to a constant. So it just becomes r squared d phi squared plus r squared sine squared phi d theta squared. That's the pullback metric on the sphere from the larger. In other words, what I'm really saying is it's a restriction in some sense of the Euclidean metric to the sphere, right? But it would totally agree with the Euclidean metric in as much as you just compare it to points on the sphere, right? Yeah.
Can you give us the function you'd be pulling back under?
So, how about you guys give it to me? What should I do?
X is rho cosine theta sine
Yeah, f of what is it? F of phi theta equals to, I don't know. That's not what I want. I guess I just want rho
rho constant. And then you take the
I mean, fine. F of x comma y equal to x comma y square root. There, let's get nuts.
yeah.
I can pull back under that map. That's a possibility, I guess.
Just take the exterior derivative of those terms, right? Dx.
I don't know. I'm being dumb here. There's something much easier to do. It is really the restriction of the Euclidean metric to the sphere. That's a what? Yes, Preston.
This is not what you're talking about right
Oh,
now. Is this
man.
how we make the sphere flat?
We're getting there. You're getting ahead of my story, but yeah. This sphere is not flat. We don't even know what flat means. Right?
It's true.
Yeah. I mean, Euclidean space is flat. That much everyone can see, right? Whatever flat means. Like that, yeah.
Just do it by, you find dx by finding that like on dx, dy is equal to 1 to dx squared.
Yeah, I mean, so we have the sphere of radius r, right, is a subset of R3. So I can talk about the inclusion map from the sphere of radius r to R3, right? And if I pulled back the Euclidean metric under the inclusion map, I think that is what we have, yeah. How dare you? I will not talk about Yoda in here. I like to have the I. Fine. I don't like it. Do you like that? I hate that symbol. Yoda. It's this. This is this. And Preston's reasons for complaining are not altogether, like his reasons are illegitimate. This is just a pathway to a certain joke he wants to tell, I'm sure, or a family of jokes, really. Okay, so I don't think I need all this. I mean, you could, listen, there's tons of different maps that have their domain as the sphere and their range something else. But certainly the Euclidean metric is defined here. I'm arguing that the concept of pullback extends past wedge products to other things. And it just means that we substitute in whatever defines this into the things we're pulling back from over there. So in this context, it just means put rho equals to r, right? The pullback amounts to that. Yeah. Okay, so great. Now, where was I? You guys have distracted me a lot. It's good though. It's good. Okay, so I would argue that this is the sort of natural notion of geometry on the sphere, is the notion of geometry which it's inheriting from like the three-dimensional space which it's immersed in, right? That's kind of like the most sort of naive concept of what we'd mean by geometry on the sphere, right? So this is the induced metric. Of course, example 2, we could talk about, a cylinder, right? Which would be r equals to r. And then we'd have ds squared is equal to what? Right? R squared d theta squared plus dz squared, right? And check this out. If I could rewrite this as like dy1 squared plus dy2 squared, if I simply let y1 be r theta and y2 to be z. I didn't really need to do the whole z thing there. All right? But look at that. What's the deal? In local coordinates, the cylinder is very different from the sphere, isn't it? Yeah? Even the induced metric, what does it resemble? R2, right. This is like, if we write G on the cylinder, it's, the sum over I and j equals 1 to 2 Kronecker delta ij dy1 dyi tensor dyj. I mean, this formalism is a little bit overkill here, but my point to you is the same formula as the Euclidean metric. When I took a course in general relativity, this is how we define flat. We define flat, a metric, we defined a manifold, a space to be flat. It's flat space if it's possible to choose a coordinate system which puts the form of the metric into the Euclidean form. If you can do that in a Riemannian manifold, that makes it a flat manifold. Now, that's a fine definition for like a physics class, but it's a horrible definition for us here. All right, we could do much better than that, right? But this is a question like, okay, so it was fairly obvious to make y1 equals to r theta to make that happen, right? Example 3, cone, z squared is equal to x squared plus y squared. Like that's a 45-degree cone. This is actually tantamount to saying that the tangent, well, what it's saying is that your angle phi is pi over 4. All right, that's actually what that means. And as such, the the metric on the cone you can write as ds squared is d rho squared, plus rho squared. Sine of pi over 4 is squared, it's a half, yeah? And d theta squared, yeah? Now that sure looks like a lot. I mean, it's not exactly like the sphere, but it looks like it might be in the same category as the sphere, doesn't it? Because it's not at all obvious that there exist coordinates like y1 that you can rewrite this as dy1 squared plus dy2 squared for for rho not equal to 0, of course. But there are. I spent many hours trying to find these. I never could. I had to ask a friend, and she's like, it's just blah. And I'm like, your brain's not the same as mine. No, not my wife. It's Manuela Kulakzizi. But anyway, yeah, so once you see it, you see it, but I don't remember them at the moment. It has to do with like just, well, that's let me not get distracted by that. So the point is, all right, well, this definition I saw in my physics course, it's kind of easy to understand, right? That there exists a coordinate system that the metric becomes the Euclidean metric, but there's got to be a better way to categorize when a manifold is flat, right? Now, again, to categorize a manifold as flat, we have to have a manifold paired with a metric, right? It has to be manifold paired with a metric, because we'll also see that if we had a mapping, for instance, if I had a mapping from like the sphere to the plane, right? And if I have that map, let's just call it F for the sake of discussion. And if I was to say G tilde on the sphere is equal to F pull back the Euclidean metric, right? If I was to pull back the Euclidean metric over here, up here, then this G tilde would not equal to the induced G that we just talked about. This would give the sphere a different notion of geometry than the induced geometry from three-dimensional space. In fact, in this case, the sphere would be flat. So this thing we can do about pulling back metrics from one space to another, it gives us a way to put all kinds of weird new notions of distance on the metric. And another thing you can do, another thing you can do is just you could take like the plane right? And you can make G equal to G Euclidean. Well, let me just do it this way. Dx squared plus dy squared. And you can divide by like h squared, where h is not equal to 0. This will still be a metric. H is like a ruler. So you're just explicitly changing the length along different spaces by dividing by a scale factor. That gives yet another, and if you did that, it turns out that this is also not usually a flat space. It's the plane with a different geometry. You can make the plane, so you can do the other thing too. See guys, you can do the other thing too. You can go, well, if f goes this way, right, then f inverse goes this way, right? So I could also do like f inverse, pull back the, G-induced sphere a la example 1. I could pull back the example 1 sphere, and that would give me, a, G for the plane as, curved space. In other words, it would be the plane with the sphere metric. It's really weird. So the possibilities here are endless. A set in and of itself doesn't have a notion of distance. We can pull back metrics from one set to another and modify their notions of distance. All right. Okay, anyway. I'm just trying to give you a sense of like what's out there.
Flat circles.
So there's a theorem in chapter 8 of Rentland, which I think is worth for us to talk about, which starts to get at the some of the heart of the matter. And this is theorem 8.2. The proof of every smooth manifold admits a Riemannian metric is actually on page 194 of Rentland. It is literally 3 sentences. Would you like me to read them? Would that make this lecture better?
Yes.
Let rho sub I be a partition of unity subordinate to a locally finite open cover U sub I on M. Let H be the Euclidean metric on Rn, and define Gi to be the pullback under the partition of unity of the Euclidean metric, where phi I is the coordinate map on Ui. Then G as a sum over rho I Gi is a Riemannian metric on M. That better? So what that was saying is that if it is if it's a smooth manifold, there's a partition of unity on it, which is to say that there's a collection of functions that have domains which cover the whole space. And whenever those domains have an intersection, the partition of unity is such that the sum of the values of the partition of unity on any place where there's an overlap sums to 1. So every point in the manifold, when you add together the things in the partition of unity, you get 1. So then you can use that partition of unity to like you can use those maps to pull back the Euclidean metric onto the manifold, essentially. And it has to piece together in a smooth way because of that construction. I could have not said this and we would have been right where we started before I said all these things, right? So you need to study a bunch of stuff to really appreciate that, and that's fine. Theorem 8.2. I should have resisted I should have denied you guys. Oh well. You're glad I said it? Okay. A frame field, all right, a frame field, E sub A, all right, is locally holonomic, meaning a coordinate frame field. I guess it doesn't, for example, a coordinate frame field, if and only if the Lie bracket of EA and EB is equal to 0 for all A and B. All right. Okay, so here's the proof. First of all, if EA is equal to partial XA for some local coordinates, right? Then what? Of course, the Lie bracket of EA with EB is nothing more than the Lie bracket of partial XA, partial XB, which we know works out to 0 because partial derivatives commute, right? Partial derivatives commute. Conversely, suppose we have a frame field that satisfies the hypothesis of the theorem. So conversely, suppose that you got yourself EA and EB equals to 0 for some frame field EA, right? I mean, it's not, when I say frame field, what that means is, bless you, E1, E2, all the way on out to En is basis for basis for tangent, basis pointwise. Sometimes when people talk about a frame field, they might be insisting on like orthogonality of the frame. I don't think that's the case here, all right? So one way you could define a frame field on like Rn, for example, would be just the pointwise assignment of an invertible matrix. An invertible matrix has n columns, each of which is non-zero, right? Collectively, the columns in an n by n invertible matrix are linearly independent. Every n by n invertible matrix is a basis when you think about it column-wise. It's a basis for Rn. So if I had a smooth assignment of an invertible matrix at each point in Rn, that would be the same as saying I have a frame field on Rn. There's an interplay between assignment of a frame, that is a set of linearly independent vectors, and assignment of an invertible n by n matrix. All right, so that's what we mean by frame, is all I'm saying. So we're assuming that the frame field here commutes, right, with respect to the bracket. And so he says, next up, let theta A be the coframe field. What's that about? Coframe field. All right. So the way that works, of course, is, you guys tell me, what's going to be theta A on EB? How's that work? What we got?
Kronecker delta AB.
Kronecker delta AB. Very good. Okay. So then what? Well, then he uses that formula that was the hero last class as well, right? That d theta A acting on EB, EC is equal to what? It is EB acting on theta A of EC minus theta A acting on theta B of EC, I believe. Uh-oh, yes.
Why is that?
Oops, my bad.
Down and then theta A is
Oh, just a second. It's all just all nonsense here. Uno momento. I've lost track of my thetas and my e's. This is supposed to be EC, and that's an EB. And this was theta. Oh, I think the A is supposed to be up. I'm sorry. It's because I lost track. I'm sorry.
Is the theta A at the beginning supposed to be up to there? Is that theta A?
Yeah. So we have E, B, theta A, lower C, minus EC, theta upper A, E lower B. And then there's one other term, right? Minus theta A acting on what? Well, the commutator, right? So what is this exactly equal to?
Well, we have the last term is 0.
The last term is 0. Very good.
Still the same.
And of course, theta A is, by assumption, a coframe. It's a covector, right? So it sends 0 to 0. It's linear. So this is 0. I mean, this is Kronecker delta AB, right? And this is Kronecker delta AC. The larger point that is it's either 0 or it's 1, right? But the constant function 0 or 1, when you act on them by the vector EB or the vector EC, those are 0. Everything's 0 here. Equals 0. So listen, it could be that if we didn't have this commutator over here, if this wasn't equal to 0, then this didn't have to work out to 0, right? These two things would always be 0 for a coframe. You give me a frame, I can calculate the coframe, all right? Which is just to say, point-wise, you calculate the dual vectors to the vectors. This is always possible. You give me vectors at a point, I can find the corresponding dual vectors, the dual bases, according to this usual definition. We just do that point-wise. Anyway, so these parts would always be 0, even if we didn't have the frame which satisfied the commutator condition. But when we satisfy the commutator condition, we have what? We have the d theta A acting on EB, EC is equal to 0. But EB and EC, they form a basis for the tangent space, which means that this d theta A, it's not just 0 on this pair. This pair is completely arbitrary. So this implies that d theta A is actually equal to 0. Which is to say that it's closed. All right? So then, locally, what can we do? There exists x sub A such that what? Theta A is equal to dxa. The theta A is a coframe. It's a one-form field, and at that point close by, I can write theta A as the differential of some x sub A's. But what does that all mean? Well, using those xa's, this is by Poincaré's lemma, right? That we proved. Remember? That happened. Then if we have dx1 wedge dx2 wedge wedge dxn, what do you got? And I think this is very interesting in this proof because it illustrates something I'm not teaching in here yet, and I should be, I think, which is how do you see the inverse function theorem at the level of wedge products? Here it is. So dx1 wedge dx2 wedge dxn, right? That is what? Theta 1 wedge theta 2 wedge wedge theta n. Now, how do I know that the wedge product of theta 1 through theta n is non-zero? Because it's a basis, right? It's the coframe to a basis. But yes, it's because the dual basis is a basis, and this happens pointwise. So this is not equal to 0, which means that this is not equal to 0. Which, as he says here, he says because that's not equal to 0, So by the inverse function theorem, that's what he says, by the inverse function theorem, the x sub a form a good set of local coordinates. And by duality, right, by duality, the e sub a's have to be equal to partial x sub a, right? Because we know that dxa partial xb is Kronecker delta ab, right? And if that's the case, and the EA is playing the role, EA with theta b is Kronecker delta AB, right? EA with, and EA is partial XA, well, excuse me, theta A is dXA, so it follows that the E sub A's must be, in fact, coordinate derivations. And so this is what we mean by a frame being holonomic. A holonomic frame is one which can be understood as being a coordinate derivation frame. So what I'm saying is that it doesn't have to be, it could be hidden, right? So what I'm actually claiming over here is, like, if you look behind the curtain, so to speak, sorry, I don't have the words yet. So let me go on. All right. So definition. If you have a frame, EA and EB, the commutator of it can be written as, I'll put a summation. He has an implied sum here, but I'll put the summation for you guys. So C, well, we've got C as an index and as a thing, but we're going to deal with that. Sorry, I'm not going to be able to unsee that, but if you see what I mean. Sorry, it's so horrible. But these are the so-called structure functions. Structure functions of the frame EA. All right. So I want to tell you guys about covariant derivative, but I don't want to get carried away with it. I'm not sure how that can be done. The covariant derivative is a way of differentiating things on a manifold. So, like, basically, let me just tell you the properties of it as briefly as I can. The covariant derivative in the x direction of a sum is the sum of the covariant derivatives. The covariant derivative in the x direction of a product of a scalar function times a tensor t. It obeys a kind of product rule. F times the covariant derivative in the x direction of t plus x acting on the function, as we've talked about. A vector field acts on a function to give me another function, like that. And also, we have the covariant derivative of a function times x plus another function times y down here acting on a tensor t is equal to a function times the covariant derivative in the x direction of t plus that other function times the covariant derivative in the direction y of t. So this third thing is what distinguishes it from the Lie derivative. This is the so-called, it says property C3 distinguishes the covariant derivative from the Lie derivative and allows us to build tensorial objects from the covariant derivative. And there's a couple of other things that you want. Like the covariant derivative, when it just acts on a function, it should just reduce to the vector field acting on the function. If you have the covariant derivative acting on G of, oh man, oh phooey. Well, I can't, the other two things I can't talk about because we didn't talk about them. All right, so it's going to stop there.
Happenstance, so it looks like.
Anyway, if you would like to see the unredacted version of covariant derivative, if you look at page 182 to 183 of Rentland, it's there, all right? But I mustn't go past this point. So the covariant derivative, guys, is the manifold version of differentiation of a tensor. It gives you, like it's giving us another tensor of the same type. Like the covariant derivative of s plus t, or just the covariant derivative of s, is another tensor of the same type as s. So if I take the covariant derivative of a 1 form, I get another 1 form. If I take the covariant derivative of a 2 form, I get a 2 form. If I take the covariant derivative of a, symmetric tensor, I get a symmetric, on down the list. So anyway, it turns out that the covariant derivative, well, this is a definition, EA of EB, so the covariant derivative of a frame in the frame direction, and I'm gonna put a sum over C in here just for you guys. Sum over C, it's not in Rentland. Gamma C AB EC. So these are the so-called Christoffel symbols. All right. So I'm just going to show you. This is equation 8.38. It tells us that if we lower the index on the Christoffel symbol, like this CAB, and by the way, all that up-down index stuff, it's still at play here. We just do it pointwise because we've got a metric. We can find the inverse to the metric, and so we can still raise and lower indices. But we may actually raise and lower indices a different way at different points because our metric has a variability. It depends on the point. Anyway, so this is, hang with me here, it's a little bit a long expression, but we got EA GBC plus EB GAC minus EC GAB plus CAB, rather CCAB, CACAB, minus CABAC, minus CABC. All right. And so the theorem 8.6 says the Christoffel symbols are uniquely determined by the metric tensor and the structure functions. So the metric tensor is the G. Structure functions are these C's. You notice that they're coming from the Lie bracket of the frame. If in a holonomic basis, in a holonomic frame, right? The structure functions, what do we have? C.
0.
Yeah, CABC is 0. So in that context, we have what's typically denoted, well, here we go, gamma Kij, it's equal to 1/2 G, JK, comma I, plus G, I, K, comma, J, minus G, I, J, comma, K. This is the formula for the Christoffel symbols in a coordinate basis. And all right. Are you ready? Here we go. R, I, J, K, L is equal to, watch this, gamma, upper I, lower LJ, comma K, minus gamma I, lower KJ, comma L, plus gamma I, KM, gamma M, LJ, minus gamma ILM, gamma upper M, lower KJ. Oh, the M is summed over, of course.
Oh, sure.
Yeah, that happened. So guys, this right here
Satisfied the Riemann.
this is the Riemann tensor. The Riemann tensor is formed by this. Now, by the way, you probably should be wondering what on earth I mean by comma K here. What does that mean? So like G, I, J, comma K is notation for partial G, I, J, partial X, K. Those are partial derivatives.
Your tensor is defined in terms of partial derivatives.
Yes. So first of all, this Christoffel symbol up here is not a tensor. In fact, if you look in the book, there is an exercise, which I don't think I assigned because I'm not a monster, believe it or not. But exercise 8.4 on page 203, it's the counterpart to the one I did assign you to see that the derivative with respect to the coordinate, right? If you have a vector field and you differentiate with respect to the coordinate, that's not a tensor because we had that second order piece, the second order derivative piece that appeared and we couldn't get rid of. It turns out that if you adjust that formula by adding a term which is contracted across these Christoffel symbols, you can get rid of that second order piece and maintain the tensoriality. That's what this does. Actually, like the formula, up to the limits of my memory, which are questionable at best. But if I did like this, partial I of, let's say, vector v, and I calculated like the ith component of it, it's something like partial j vi plus gamma I j l vl. All right, now I gotta put some scare quotes around this, guys, because like I haven't checked conventions. I'm not sure about plus or minus here. But like this is literally how you modify the coordinate derivative to make it into something that's tensorial. Is you just add a piece with the Christoffel symbols, and this will end up giving you something that transforms as a vector. That's what the covariant derivative is, if you look at it in terms of formulas. But anyway, yes. So first of all, the Christoffel symbols are formed from